Okay, so good evening all. Today is day 7 of our training. I I welcome you all and happy to see you all looking at day 7 of the training. I really appreciate your efforts and seriousness in learning. So today our agenda is to know the different versions of development of FPGA chip based on the IPs. So as I have introduced IPs in the earlier sessions, now today we will actually see into the IP integrations. So in the Vivado tools, we have advantage of using the block IPs that are actually generated by the vendor companies, and we can directly use these blocks, and we can implement the design from it, and we can run the simulations, and we can test it on the FPGAs. So it is a different process, guys. So since yesterday we were writing traditional script in Verilog HDL or VHDL, and then after writing a test bench to verify it, and then coming to the simulation part, we have simulated the logics of the OR gate or AND gate using timing simulations. Today we will do it a little bit different. Let us go to the session. So today's agenda. What is today's agenda? So designing the RAM and using IP configurator. What is RAM? You all know random access memory. It's a memory block. So today we are developing memory block on the FPGA chip. So how do we do that? Let us go to the today's session. So use of IP manager. By the use of IP manager, I will show you the list of IPs, and here and there I will switch between presentation PPT slides, and then I will take you to the tool as well, to the live demonstration. It has already been done by me, and if you do the process in the step by step manner, and if you follow along with these slides, you will complete the development on the FPGA chip using IP managers and IP integrators. So think of this type. Now we have all the blocks ready, and we are connecting those blocks and making a process or making the functionality or developing an application of storage. So like memory storage thing. So kind of getting the functionality on the FPGA chip, implementing the FPGA chip functionality using the memory blocks. So today we have used memory blocks, and later we can use some display configuration or any other ability. So LCD display you can add, and you can add some counters or ALU logics or IP. Different types of IPs we have in the FPGA Vivado tools. So every EDA tool has this kind of IP licenses and IP managers. So we need to check whether the license is available for that particular IP that you are using to develop on the FPGA. So this is the second methodology of developing on the FPGA. First one we know, developing the architecture using VHDL or Verilog HDL script, and now we will be developing the scripts using blocks, IP blocks. So designing the RAM and using IP configurator, use of IP manager, blocks and connectivity. I will make you understand all these things, and a little bit of block RAM introduction. I'll introduce you to the memory block as well. Today it's an IP, and in industry you might work with bunch of IPs and you will get to know. And if you dive deep down to the each IP, and if you understand the architecture inside it, how they are connected, and those can be seen in the FPGA design that you get after the design implementation. So I'll take you there as well. Yesterday we have viewed a few of the internal cells and the blocks that are available in the FPGA chip that we are using on Mars AX3 board. So again, simulating the BRAM memory. Every time when I say simulating, guys, it might be the last step to verify. So as I said, understand this. In the FPGA development or in the use of EDA tool, now we are getting to know a process called synthesizing, design implementation, and then simulation. And then the simulation part is nothing but verification of the data. So as we have this block RAM today, and we will be seeing the data that has been come over the output. So I'll make you understand each step in deep down. So let us go to the uh, session. So as we all know, when we click on Vivado tool, open up the tool, and you need to create a new project. That project is nothing but click on the create project, and when you click on the project, you will go to this window. It is same as you have been doing this for the last 6 days. It is the same process when you create a new project. Whenever I say project, this might be the third project that we are doing in this training as of now. So this training is based on the project based learning. Everything you learn, you need to implement and learn through the practical experience. Until you accomplish practical experience, there will be no surety or confidence that you gain out of this training. So this is a project based learning. So now we are going to the block RAM memory development on the FPGA. So create this new project and go to the project name. Let us say project underscore to underscore IP. Here I have mentioned 2. You can mention project 3 because AND gate is the first project, OR gate is the second project. In the second project, we have gone a little bit far in the development. I mean, we have implemented till end. We have generated bit streams yesterday, and we have also uploaded it into the FPGA board. So it's a complete flow. But in the AND gate, we got an introduction to the Verilog VHDL scripts and Testbench VHDL scripts. So after you create this, now in this window, earlier we used to only check for the RTL projects, but today we do not want to specify sources at this time. Means we are not insisting the um, tool to assign any sources. So let us take that part into our hands. We will be specifying the sources at what time we want in the design development. So same RTL project, you might also know what is RTL project. In the RTL project, we have bunch of things. One is IP integrator, generating IPs, run RTL analysis and synthesis, and implementation and design planning and analysis. This is what the flow that we are doing. Analysis of the Verilog HDL or VHDL scripts and synthesizing it. Synthesizing means assigning the pins, ports, and connecting the elements through nets and generating a netlist file. After synthesis, the generated netlist file needs to be implemented according to the FPGA board. So in the design implementation, we check the ports and pins connections accordingly, and then we go for design planning. Planning is nothing but assigning the ports and pins. Yesterday we have done that for OR gate. We have assigned LED for the output C port and buttons B1 and B2 for input A and B. So that's how we go for the planning, and analysis is nothing but this is a simulation part. On the simulation window in the timing simulations, we have checked the functionality of OR gate, and today also we will be checking the data transmission. If you have given some data, random data, and it should go after some period of time, after some clock cycles. So we will understand how we can develop a block or IP FPGA chip using the block or IP. So this is a design development of FPGA chip, not from the Verilog HDL or VHDL scripts architecture. We are using the actual architecture that is already available. So we are taking directly the block and we are using it. So for that, we need to select the board. It's a usual task. You can select subfamily or you can leave it. When you say CSG 324, you can see the board, and speed grade should be 1. It is an optimum level. That's what we work on. You can select subfamily as RTX 7 as we did till yesterday, and from today you can keep these things as it is, product category, family, subfamily, all these other elements. So you can leave it as it is, and then we can go. So why am I changing these every day? So because you need to be flexible enough. You would never know whether you get a board of your desired specifications, but in the industry you will be working irrespective of the board. Whatever board you get, it will be working on the boards. And if you know some specifications on the board, for example, what is the clock speed and what is the number of availabilities of lookup tables, what are the number of flip-flops, all these things will be known. And then depending on the specifications and the architecture, how many lakhs of transistors or logic gates you want, you will be getting the specifications from the specifications vendor. And then from that specifications team, you need to develop the RTL project, and that's what we are developing now. From this RTL file is nothing but registered transfer level language file, and that file will be in the terms of VHDL or Verilog HDL format. So now if you say VHDL script you are developing the actual architecture based on the specifications on the FPGA chip. So today we are not doing that process. We have changed our methodology today. We will be going for a block design from the group of blocks. These blocks are again IPs. IPs are nothing but intellectual properties. Where do we get the intellectual properties? Yes, that's a good question. Intellectual properties will be coming to us from the different group of vendors or different group of companies. Some companies might work on memories, and some companies might work on only displays. Some companies might work on the actual logic operations like arithmetic operations and unit, which does the calculations part, and some does the part of buttons interface, or some does the part of peripheral interfaces, and some IP vendors have done the part of uh, different elements or parameters or any elements that are available on the FPGA chip that has the functionalities. So we can use different IPs and we can make our desired chip. Like it's like connecting the blocks and generating a architecture after connecting the blocks. It is like making our life simple through automation. So I will show you a little bit, and I won't be writing any VHDL or any other thing. Tool will be giving me VHDL after designing the block. So yeah, this is the summary, guys. You can see it has already taken the Arctic 7 family because we have mentioned CSG 324. That's a package name. We go through the series, and default part XC7A 100 TCT CSG 324 bar 1. And you can remember this as it is to mention in your resumes as well. We have worked in the Arctic 7 processor and Arctic 7 FPGA, like FPGA named Mars AX3 FPGA, and this is the processor. And we have worked using Vivado EDA tools provided by Xilinx. So now click on finish. You will see the Vivado EDA tool window, and in this window you will see the sources, and these will be the sources in the design sources and constraint sources and simulation part. And you see this window. Now let us go to the creation of the block. For that we need to add an IP. How we can add an IP? You can click on the create block design from the IP integrator. In the left side menu there is an IP integrator. So in the project manager you have created the entire block source, entire the file sources and all. You have mentioned the project directories, and then you will be going to the IP integrator. There, if you click on create block design, earlier we used to give add sources. So we used to add the source. How did we add the source? We have added VHDL script for AND or OR gate. But today we are not doing the source of VHDL adding, and we are adding the block. Now click on create block, and then we go to the window which says we need to mention the design name BRAM. As we say in the VHDL source, if you have followed along every class till today, you can relate some things. Like in the source VHDL file, you can see the entity name where you are declaring OR underscore gate or AND underscore gate. In the same way, when we click on create block design, it is asking for design name. Okay, now you need to design, you need to mention a design name which is an entity. Entity is nothing but a device, or entity might be an device name, or entity might be a block name that you are using. So now mention VRAM and leave all the sources as it is, and okay. So click on OK. It will take you to this window. Make sure you have opened your diagram window. In the design, it will open a design here, and after the sources, and there will be scope in the later stages, but in the sources and design, you need to go to this window, right click here or click on somewhere, and you can add IP. When you click add IP, I'll show you in the Vivado. Okay. Yeah, when you click on IP, you will be taken to this type of window. You can search here for block memory, or you can go through the different types of IPs. These are all IPs. IPs are intellectual properties which have predefined VHDL code that are already available, and this block is ready to use, but we need to enable it by selecting it and reusing it on the FPGA process. So when you select it and implement the design with BRAM, then your entire FPGA chip will act as a BRAM. So all these IPs are available in the EDA tool, and you need to attach these IP blocks to the FPGA. So like it's a mapping thing. So now block memory generator. Uh, so click on the block memory generator. Today, okay. So today it's block memory generator, or in the industry you might go for some CIC compiler. Okay, now your FPGA board should work as a CIC compiler, or clocking wizard. Clocking wizard. Okay, it should work for only clocking. So these are bunch of IPs which can accomplish your entire application. If your application is like run this FPGA chip into a supercomputer, and then computer should have all the IPs. What all types of IPs? UART protocol it should have. USB 2 device it should have. Video directory memory access it should have. Virtual FIFO controller it should have. Binary controller, obviously it will have for different set of controllers, or different set of counters you design. So counter is a basic thing for the clocks, and color correction matrix, everything. I can scroll a little bit, but this is how you go through. Just if you go through this window, go to these different sectors and then check. Let me open some one here in the diagram. If you click on this diagram, this is our block rank, and if you click on add IP, now you can see this window. Maximize it, right? I can maximize. So look at here, guys. Yeah. So see your FPGA chip. Inside that FPGA chip, you can add different types of functionalities. What are the different types of functionalities? You can add 2.5G Ethernet, like you can attach a Wi-Fi module and it can select Wi-Fi signals out of your routers in the home device, and now your FPGA has internet. Kind of these IPs you can add, and AXI interface, it's a transmission interface, and data FIFO, first in first out, and data with converter, everything. You can see bunch of IPs, but only some of these IPs will have the licenses according to the Vivado tool or the EDA tool that you installed. Don't worry about those licenses and all. And now you can see block memory generator. And in the same kind, you can also add different blocks. Now we have one block. This is block memory generator. For this, you can add input and output. anyway, it has input and output. But what we are looking at is we can add bunch of blocks here, and if we can connect into a single application like in the control systems, and that entire application or the functionality logic is made into a chip functionality, so by the FPGA mapping. Now we can have the processor as well. Microblaze is a processor, and memory interface generator, it's again another different types of memories. Multiplayer, multiply adder, multiplayer, simple multiplayer application. And uh, what additional things you, video on screen display, kind of these IPs you can attach. And YCR CB to RGB color space converter, kind of, if you have LEDs, and it can be also used. And video scaler, video timing controller, these are depending on the project specifications. In the industry you will be going through these different types of IPs. So come back to this, and you select block memory generator and block memory generator. Now you will see a diagram here, and when you see a block, these type of IPs will be sitting on the diagram. So when it says diagram, right, that diagram is like you're drawing the blocks, connecting them with the wires, input, outputs. And if you check the functionality manually, you can check the functionality by giving the data, and you can process the data, and you can calculate the delays. Everything can be done in the paper. In the same way, in the diagram, if we are dealing with one block today, and in the industry you might deal with several blocks, like tens to hundreds. It depends on the design, how complex design you are designing for 2 to 3 years or 4 years of the chip processing. And that might be a future chip. It should be ready for the future generations as well, and it should achieve speed, performance, and power optimization. Area as well, that chip needs an area as well. When I say area, it is a different scenario in the IC designs. But now we are dealing with one block, and double click on it. When you double click on it, this customization appears, and this is the window for block RAM. You can see the different ports, and these are all the pins available for the block RAM. It's a 32-bit, and you can use 32-bit interface for it in the inputs and address bits. And in this thing, what are the elements that you need to change? You need to change the basic port A and other options and summary, but we only change few of them. Rest we will be setting the default values as it is given by the EDA tool. So then basic port A, in the port A you can see the write width 32, the minimum range, and write depth, let us set it for 8192. Write and read, it's a depth is nothing but these many number of bits it can acquire, it can specify. So those bits can be going beyond that wire inside through it, and you can't make more than those number of bits. So let us write it for the 8192. And again, other options, you don't need to change any other thing. Summary you will get, this is the summary. So total port read latency, so you can check 1 clock cycle. I'll show this 1 clock cycle in the simulation window in the next thing. Let us go to this. After you click on OK, right, and you can see this kind of window. You have address, clock, data in, data out, enable, reset, right? So everything is right enable, right enable. So everything here in the pins are basic versions of the pins for any block. For any block means some might have data or some might not work with the data. Everything goes with the signals. Whatever signal comes through the address bus, it might push forward to you. Those are very basic applications in the blocks. But now you can see address pin, clock pin, data in, data out. You can see the data in as 3120, like it shows this size. Remember guys, when you see the square brackets and inside this kind of syntax, this is the size of the bus. Many of you might not know, but this is the size of the bus. Please make a note of this kind of elements. You might get doubts afterwards. So now you can give the data input as 32. So 32 bit bus interface. So when you connect a wire, it should have a processing capability of 32 bits. So now to check this IP whether we have license or not, as I told earlier in the introduction, to give the authenticity on the block that we are using, that yes, this block has an IP. Now we can check the tickle command in the down below. You can go to this tickle console and you can check report underscore IP underscore status. So this is a tickle command. What is tickle command? Tickle is nothing but a command language that we give a command or instructions for an EDA tool to check or to verify some things and to acquire some reports and summary results of all the process or the design implementation that we do. So in those kind of tickle commands, one command is report underscore IP underscore status. Mostly guys, Tickle is wide rangely used in ASIC applications, ASIC designs, like in the chip design industry, because ASIC chip design is based on the EDA optimization. And for the EDA tool optimization, we need to run the design or actually design some specifications based design, chip design. We need to we need to develop the chip design using EDA tools. And how will you do that? We will write set of commands in Tickle scripting language, and that commands will set the EDA tool to do the process in an automation. For example, if there is a command called uh, for example, it's a very basic kind of example, like uh, open open underscore some EDA tool. You might not know, and you haven't heard of this ASIC tools. And you can say you can invoke you can invoke the tools from ASIC design. EDA tool, EDA vendor by Synopsys or Cadence have different EDA tools, and each tools are used for synthesis and RTL designs, and also for design implementation, place and route, and verifications, physical or logical verifications. And also we check the static timing analysis, that is a timing part. So these tickle scripting, or you also might have heard about Perl scripting, those are in the design tools in the chip designs. So go to these and search for what are these applications. And simple explanation is give the command and make the EDA tool to design your chip and verify this chip functionality again with the tickle commands. So you can design and you can verify. That's what we use this tickle scripting for. Report IP status, and then go to the window again. In this window, if you check the IP status, you can see this included, license included. So when you see license included, okay, it is a very good block that you can use. And for this reason, we have implemented licenses when we install. So it's a crucial part. Then go to the window again, this EDA tool. In the top, when you scroll top, and in the block RAM, in the design sources, right click on it. And now you need to create a HDL wrapper. So coming to the next major step of this entire design, you have created files, you have added IP block. Now we need HDL script. Why? Because block cannot be changed into bit streams. But yesterday we noticed HDL script, we have made it into bit streams. Understood guys? And also to check on the IPs, we need to check with the test bench. Anywhere we check VHDL with Testbench source file, we check the architecture with Testbench, or we check the block IPs with Testbench. So this is a different methodology today, and we have created an IP block, and from this we can create a VHDL. So it is an easy task for a different complex projects, and you should have both the skills, writing VHDL and making blocks, and uh, getting the IP blocks and generating HDL is another level. So you need to have both the skills in the working industry. You might not know, you can only have a limited IPs, but you might require some other blocks that you should design on your own. Got it? So in that way, you need to write the architecture using VHDL, also develop the architecture on the other hand with IP blocks. So I hope you understood. So writing the VHDL script and making the architecture on the FPGA, and also some part like you need to get the IP blocks and creating the VHDL or Verilog HDL script out of it. How do we create VHDL script out of IP blocks? Same way, you go to the design sources. You see this window sources. You need to click on the sources here down below. On the sources, click on block RAM design. Right click on it. BD is nothing but block diagram or block design. Dot BD is a block diagram or block design. So right click on it and you will see this window appearing. And if you click on create HDL wrapper, right, it will create with some window specifications. It will ask you for create HDL wrapper thing. And if you click on create HDL, you can either add or copy HDL wrapper file to the project. Use copy option if you would like to modify this file. Yes, okay, copy option. Copy generated wrapper to allow user edits. One thing. Let Vivado manage wrapper and auto update. No. We are not giving full access to the EDA tool. We are taking the control on how to edit the wrapper. Wrapper, guys, it's an HDL file. Don't get confused between two different names. Just understand wrapper means, okay, it has been made out of the IP block. Already some guys who have written the IP block and they have made the draft of VHDL and sitting in the EDA tool. Now we are taking the draft file. Imagine taking the IP, and when we take IP, it comes from VHDL script written by some IP vendor. Now it is a draft. They don't know the input ports, they don't know the output ports, they don't know what pins to be enabled, what pins to be available for your IP. Now you have designed input pins, output pins, and like this. You have designed all these things on your own by the specification. When you selected the IP, right, this comes with this. But you can also alter the design. And when you design all these pins, these should be declared in the VHDL script. That is the reason they made a draft. When you click on generate HDL script, from the draft, it will assign all these pins. I will show you the VHDL script. You will understand. But imagine taking IP block and declaring the pins for it, checking the pins, and all these pins were not assigned for the same VHDL file for a block. So now this block VHDL file has a draft, and for the draft, if we click on generate HDL wrapper, this has all the input pins and output ports that are defined automatically. So copy generated wrapper to allow user edits. When you click on OK, now it will generate the HDL wrapper, and it can be named as VRAM underscore wrapper.vht. Now we got wrapper.vht. When you click on VRAM underscore wrapper.vht, guys, if you want this VHDL files to verify, I mean, you can verify my VHDL file and the file you have generated. It should be same. For that reference purpose, if you want, just WhatsApp me or text me that I can give you directly. But I need to talk to you first. So thank you for approaching again in advance. So go to the HDL and check the generated VRAM HDL file. Now let us check. So there is a VRAM.vht. Very good. Now I will be taking you to the VHDL file. So it will generate a VHDL file. I didn't write. We are not writing here. We are utilizing the EDA tool to do the major task. So this is automation, guys. Now you are understanding how we work with the automation in the chip design industry. It is a very complex designs. So for the complex designs, we need to use some tools to make it happen. For example, uh, let us take a anomaly like car manufacturing. So if we take car manufacturing, there are several parts embedded and integrated inside the car and external parts as well. Some different steps of car manufacturing is, some might be going through engine side and they work on only engine department, and some will be working on tires department, alignment and fixation of tires, and manufacturing of tires is from the outer world. So we are getting tires from some other vendors, Michelin, MRF, Seat, all these tire manufacturing companies give tires. But BMW, if we take BMW company, that BMW company won't manufacture tires. It might have tire manufacturing, that's a different channel, but it might use Michelin tires for different various versions of BMW cars, 3 series, 5 series and 7 series. That is different. But imagine today we took memory block and we are designing this FPGA functionality into a memory storage or memory operating device, RAM, random access memory. If you switch off the memory that you are working or the functionality or the process that you are working, it goes off with the shutdown. But it's not wrong. We can also get memory elements that can store the data as well. After we shut down, again if we restart, we can see the same data input sitting on that ROM. Different. We can develop different types of memories on the FPGA chip. Today we are designing RAM, random access memory, and BRAM design in the FPGA using VSRAM. Yeah. So, okay. Now take this car manufacturing. Car manufacturing has electronics embedded into the car, and those electronics should go through the AutoSAR development, embedded AutoSAR developments, and that works under CAN bus protocols and different I2C and many other protocols, AX and AXB. So all those protocols, and then wiring and power source optimization, steering wheels, and you can come for the seating, interior is also a different vibe. So you can see the glass fittings, windshields, window sides, and doorknobs, everything, every single element will be done by some thousands and lakhs of persons, and they also we automate. But in the car manufacturing industry, if you see some of the blogs in YouTube, you can find major part of the body, like for an example, welding of the car manufacturing goes from any robotics automations. One best company for robotic automation is CNC Robotics here in UK. It's a growing company, very good company in robotic automations. Like they create robotic arms in the huge industries. So these robotic arms will design or will be used in the manufacturing processes or any 3D bigger 3D designs. So yeah, so we are utilizing the tools for making this process automated, or else if these many people sit and build a single car for months and years of years, and it will take plenty of amount of time and money. But if we take use of machineries, these will be accomplished very fast. So you can see in the manufacturing industries, a chain of materials go in a flow for every minute or for every 5 minutes. It's a timing chain that goes, and then the work goes on. So that is the same way we develop the EDA automation. In general, in this environment of nature, every process can be related with different other examples, analogies. So now uh, this automation, generation of VHDL code for this block RAM is done by EDA tool. In the same way, if we have 10 different blocks, connected one by one. Those will be connected, and we can generate a single VHDL file with all the functionalities. So that we don't need to write this much. And if we make an attempt to write this VHDL file, we can write, but there will be an human error. So to remove the human error and to understand the complexity, we are using EDA tools. So it has been generated. You can see the entity BRAM wrapper. It has took into BRAM wrapper, and it has named this file. This is the file entity, and libraries it has used universal simulation. It can, this VHDL file can be used on different types of architectures. And now you can see host, that's my PC. You can see all these things, if for bit, and date, that's done. And you can do entity, port, and also, and this type of VHDL script you can understand when you relate this with the previous versions of our projects, OR gate and AND gate, declaring the ports and declaring the component ports again in the architecture. When the architecture, we need to define the component again. That component is nothing but our BRAM. Then go to this thing, and in after architecture declaration, right? So you need to go for the process beginning. What it has to do, it has to push the data for random access memory. What it does, it stores the data for few microseconds or nanoseconds, then it push forwards to the next block that is available. Here we don't have next block, and it sits in here. And what it has to be done, we need to map the ports according to it, VHDL. So everything is done. Now we need to test this VHDL file with the test bench. It is a standard process. Every time you need to stand. Okay. Now the entire script was generated with using VHDL. This is VHDL. We can also create using Verilog HDL. We might not know. Project should be flexible enough. We need to learn the flexibility of understanding the Verilog HDL. So now we can also change to Verilog HDL in the project manager itself. When you click on project settings, here project settings, click on project settings. In the general, you can select the target language as Verilog HDL. Earlier, when we have written VHDL scripts, we have given target language as VHDL. So it is okay to go with the VHDL. But here we are changing in a different way. After we generate the VHDL, we can also generate Verilog HDL out of it by clicking on the target language Verilog HDL. And you need to generate the wrapper again. How do we generate the wrapper again? Go to this part. In the design sources, click on the right click, create HDL wrapper. Then it will create Verilog HDL now after selecting target language. Or before you generate this thing, before you generate .vhd from this block diagram, block design, you can go to project settings, change into Verilog HDL, and click on it. Any way you can do. There are no limitations now. So after VHDL, go to this. This is an additional tip. This is a tip. This is not the process you need to do. Remember, guys. So now we need to go for a test bench VHDL. How do we create test bench VHDL? So create source, add create source. For test bench VHDL sources, either you can write, if you understand the VHDL in full length, and this course, in this course we will be dealing with the Verilog HDL in the near future classes, and we only deal with little bit of VHDL in the introduction in these sessions. But you can learn VHDL. You can also learn how to write test benches. There are different bunch of sources. But as of now, to make your process easy and to make you understand the test bench scripts in the VHDL, just add the source like this. 1 second. Add the source, create or add or create simulation source. We have done this. We have created test bench. You can see in the earlier sessions. And now go to the file type VHDL and file name bram_tb. This is a very familiar process if you have done the prior two projects and OR gate simulations. Now test bench is written. How do we make this test bench VHDL script? Simple. There is one way in the online. Go to the online. You can search for online VHDL test bench simulators and take your VHDL script, whatever you have in the VHDL scripts. Take your VHDL script and copy paste this entire script and use it in the online simulator to generate a VHDL. Then collect the VHDL test bench VHDL script that it has made, copy paste and copy it and paste it in the bram.tb_VHD here. Understood, guys? So now this is the VHDL script. You can write the script by seeing into this video as well. Please make a note. You can write it here, or you can generate test bench VHDL files for your primary source through online simulators. We have different sources, so there is no limitation in open source, but only limitation is we can't go beyond the certain limit of complexity in the chip designs. In open source, we have certain libraries, or we can work under the limitations of a little bit of complexity. But now in this type of basic designs, you can simulate basic test bench VHDLs, not an issue. But after generating test bench VHDL as well, you need to check whether you have clock in the design. If you don't have clock, if you don't mention clock, ignore it. You can use the basic clock inside it, and then you can use this clock design according to the EDA tool. It will be assigned. Don't worry about the clock in the design right now. I have commented it. How do we comment? By two dash, and if you enter two dash, the entire line will be commented. Line will be commented, not the entire paragraph. So same way in test bench VHDL writing, as I have been explaining since last 5-6 days, it has to go through these different type of steps, like 1 2 3 4 5 6, let us assume. So in those type of 6 steps, one, declare libraries. I'm making you understand the syntax of how do we write test bench VHDL. Libraries you need to declare, same as well in the primary source VHDL as well. Unlikely to the test bench, you understand you have primary source VHDL and also test bench VHDL for the verification of primary source VHDL. Don't get confused between two VHDL files. So in this test bench, you will declare libraries, and also you are declaring the entity and ending that entity. You are making the EDA tool to understand, okay, entity BRAM, end means you stop it here. Okay, you understand this is bram_tb. There is nothing much left in the bram entity. What we are going to do, we are going to the architectural behavioral of bram_tb and then component. This is the syntax, architecture behavioral. It will start. You need to end this architecture as well. So again, bram_tb entity is architecture behavioral of bram_tb is, you're telling bram primary source file bram.vhd, and in the same way that architecture should be in behavioral and should be checked with the bram_tb file, this entity, and component is bram block, our component is block ram, and port, these are all the ports available and was given by the EDA tool, I mean given by the IP vendor. So what are the ports again? Address port, clock port, data in, data out, enable, reset, and write enable. Got it, guys? So you can write on the block memory as well. Whenever you want to write, you can write it. I will be showing you to change the data through these ports in the simulation part. It will be easy, don't worry. So ports, after you declare ports, go to the signal part, and in the signal, it's block RAM, BRAM port A address and BRAM port A clock. So all these signals, you declare ports. For those ports, you need to enable signals. When you say signal, okay, EDA will understand and make FPGA to understand that, okay, this address bar should go through this signal power, and enter signal should be there through these ports. And this is the syntax that you need to declare whether the direction of the port is input or direction of the port is output. You have 6 inputs, 1 output. Cell, I will show you the cell as well in the design. So in the 5th step, declare the signals. 6th, now begin the process. What is the process of beginning? What do you want to begin? Begin the testing part. Till here, you are actually synchronizing the ports and signals from the actual primary source. The primary source VHDL file and the testbench VHDL file should be same. Now go to the second part of this code, begin the process. After you begin, DUT VRAM, on that VRAM you need to start the process, and port map, you need to map the ports. Simple guys, mapping ports is the ultimate step. And when you map the ports, just stimulus, this stimulus you need to create the process. That means your block RAM will be up and running. This up and running with the given inputs. How do we give inputs? We give inputs through clicking pins and ports, or through giving the input to the timing simulation. That we can do. So begin and wait, end the process. Begin and wait, it will wait and end the process. As I have disabled the clock generation, I don't want this clock generation. It is a complex topic again. It is a separate topic. It can be explained in the later stages, but understand, wait the process. Now Testbench is also done. Now go through the simulation. If you run the implementation, right, then you will get the simulation. So you need to run the synthesis. So if you click on implementation, this is timing simulation. If you click on timing simulation here, by keeping 5 microseconds, you can see the simulation runs, and for every port, I will enlarge it in the next window. But if you can change some of these ports, one is address ports, one is clock port, one is data in, data out, you will be checking this in the next windows. Don't get too much of worried. I want you to understand, you need to run the implementation by timing simulation here. So Testbench looks like this. This timing simulation looks like this. This is one input. We can change. That input is nothing but VRAM port A address port. So in the address port, right click on it. When you right click on it, you will be seeing force constant. You need to force constant, and when you force constant, that window will look like we don't have. Okay, I'll show you in here in the HDL. And okay, now if we run simulation, run behavioral simulation is already running. Do you want to close it and relaunch? Okay, already running and closing. Just run the simulation. I have kept 10 microseconds, guys. Do not worry. Run simulation. Simple. Run simulation of the Testbench VHDL. Now get down this part and open this part. You need to click control. Some of you have asked why it is showing universal. It is the infinite part. Timing has gone to the 1 lakh picoseconds. 10 lakh picoseconds. That is, again, you need to click on control and scroll down, or you can click on this navigation bar and you can come back to the starting point, and you can see some variations. And now again, if you want to zoom out, click on control and scroll down, scroll back. The timing will be changing now from this ports. And now if you can see this VRAM port addresser, and if you click on right click, you can see force constant and force clock. Now constant should be kept as 1. So apply and OK. And if you change all these things like this, in the clock, you need to force clock that leading value and 1 and leading value trading value as 0. Apply and OK. So now accordingly you will see the differences like this. So now let me take you to this. I am showing this because you need to work while looking at this screen. You can pause it here, so it is easy to use. So for the address bar, click on 1 and click apply. And for the next port addressing, remember guys, for the clock as well, you can see in the clock, when you click on the clock, you can see the second one, clock. Right click it and force clock, not force constant. For clock, you need to force clock from leading edge value 0 and trade edge value 1. I have kept 1 and 0. You can keep 0 and 1. Keep it 0 and 1. What is the difference? It makes no difference. It is that we are telling leading and trailing edge by following ones to follow along with the original things. So 0 and 1. And in the board, if you click on reset, or if you click on enable 0 or enable 1, again these values differ. So there's a tip, right? If we are developing an AND gate, and if we negotiate, I mean if we negate it, negate is nothing but changing the operation of AND gate to the other functionality, it will be verified as OR gate as well. Don't think guys. On the board, if we change the clock edge from 0 to 1 or 1 to 0, again the data signal changes, and with the change of the functionality, OR can be and can be OR. That is a very negligible change. Sometimes the error happens on the board, so don't think. But you understand the clock edge. If you are giving from 0 to 1 or 1 to 0, the clock cycle should be different. So clock cycle should be 1 and 0 or 0 to 1. So leading edge 0 first and trailing 1. So that's what it is. I will draw and show you. So first 0 and 1. This is what leading edge and trail. And now if you say 1 and 0, it will be like this. The clock starts from here. 1 and 0. 0. How will the clock available in this thing? It is like, so you can see in the next window. I'll clear all these things. Now you have set clock as leading edge 0 and leading edge 0 and trailing edge 1. First you set the force clock, right click on this thing, and if you force clock, so right click on this thing and this window will appear, and you need to set this 0 and 1. Radix is nothing but units. It should understand. EDA tool will understand the units. And go to the window, and you can see the clock. This is the clock. Earlier the clock is in the same way, it is dead 0, and now clock is enabled. It is in the 0 1 and 0 1. So after this, actually when you set this thing right, if you click on this timing simulation again, you can see the variation. Remember guys, I am repeating, in this window, first you will see this window, and if you click on right click, this window will appear, and in right click force clock, you need to select force clock and go to this window, make it 0 and 1, and then if you click on this timing simulation again with 5 microseconds, you can see the variation 5 microseconds between these two. Clock will be generated, and then remaining ports, you need to set a force to constant. It shouldn't be universal again. First you need to change the address port, right click on it, force constant, you can see 1, and for the data in right, let us give value 10 10 10, and you can see data out. You don't get the data out. Data out will be coming from the block RAM. And enable we need to enable it. Block port A, enable the port by 1, and enable the reset with 1, and everything will be 1. Write enable. Okay, so some write enable you need to do. Some write enable you need to give, and that will be 1111, or you can give any other value, some data value, and we can play with the data. I will show it, and click on apply and OK every step. uh, from this starting point, go to this clock, and then you need to change every port. I'm repeating this: address port, add one value, force value constant, and data input you can give whatever data input you can desire of, and you can see the data input data as the output as well. I will show it to you. And uh, port enable, you need to enable the port, enable the block ram, that can be enabled with the constant value 1, and reset, and again write enable. So you can check these things, and now after that you need to click on the timing simulation again. So let us do this with the help of this thing. Now I will force the clock. Here in the force clock, you need to give 0 and 1, and click on apply and OK. And if you click on again, right, it will show you the normal value. That's it. Don't worry. Apply. OK. Just enter it and go to the force constant. Now, what is the value you want? Let us take complex one, 10, 101, like 1001. Let us take either it might be 9, I think. So apply. Okay. Now data out, you don't want to disturb it. Enable this force constant. It is, sorry, I don't want to force clock. For this thing, I want force constant. It is 1, and apply. So okay. In the reset, right, go to the force constant. Again, it should be 1. All these ports of the chip you need to mention properly, and it is very simple task. Click on OK. Why are we doing this process? To verify the block RAM in the timing simulation instead of going to the block. So if we click on this minimize window, go to this, and now you can set it as 5 microseconds, and if you say run implementation, it will take some time. Wait for it. That is the reason I usually don't run the simulations here. So before second. Okay, address bar need to change. Okay, you have changed the clock, force clock, to 0. Let us check this thing. Now you can see we can change it to the 1 at this part. So let us take this part. The clock is enabled after set of timing address port we have set to 1, right? The value is 1 now. Earlier it is universal, and this, and from the 1 nanosecond of the time, clock has been generated. So for every 5 nanoseconds and 5 microseconds. Understand this, 5 microseconds. And then now we need to give the data input. Now force constant. What is the data? 1001 that we decide of. Apply and okay. See guys, this is the Tickle report console that you have changed here, and it has been applied and okay, clicked okay. So you can see the status as well. Now this is done, and every other thing, data output, you don't want to change it. And enable port, click on ok, apply. Okay, see now enable port has 1. And now what is the other force constant? It is 1. Apply. It's a reset. Now reset is also 1. And now right force is, so apply. Okay, now again you click on the simulation part. You can change, you can see the different variations to the data. Yeah, see now this is data vary from certain point after 5 nanoseconds. So you can see the data in this way. Understand guys? Clock is enabled, but after adding one more microsecond, after 1 nanosecond is added through this, uh, everything is enabled now. After enable, see the data how it changes. In the left hand side it is universal. When it goes, this is how the block RAM operation goes on. Every data, every message or every bit, it travels through the timeline of the clock. Understand, this is very much important in the understandings. So clock is constant, it has certain particular microfreq so it is 0 clock, and again 1 0 1 0, it goes on for every clock cycle. And then you can see the data changing to 1. So let us keep it here. We can enlarge this part, the data. Oh, okay, now it will be very clear. You can see the ports, right? Okay, ports. Now see the data guys. 101. So here is the data 1001. Okay, so and it is a bit, it's a register. The entire data is a register, and now for that data it is available in the output as well. Got it? What did we get here? Right enable 01, as it is same with the address port. So that's how we can show. And in this part it is same as well. You can see the data has been gone through different stages for the 15 microseconds. And now the clock, when you shrink the clock, right, it will appear in this thick green line. Don't worry about it, it is the clock again. And you can see data right enable as 111 that we have given. And output, you can see this is the same. It doesn't vary because it is not connected to the neighboring port of any other different block attached to it. So this is the device. If you go for this design example, how do we open that design? In the window, you need to go for in the, okay, you need to set, need to go for opening the design. It will be available in the window, or you need to run the implementation again. Yeah, it won't be an issue. If you run the implementation, you can open the design as well. So it takes time. Be patient. We are looking for this kind of design. Will eventually be shown. So why do we have this many values? It has 32 bit values. So address bar is 32 and also data in and data output is 32. So why there is no data output, right? It doesn't do any operation. It's a simple operation. So you can see 32 bits will be shown here in this way. So our implementation successfully completed. You can open the implementation design, and after your implementation is done, you can go for the generate bit stream, and after you generate the bit stream, you can be uploading directly to that. So reloading the design. Luckily, it will open automatically, or we need to go for the window and open the design. Okay, it has opened. Now it is a device. So you can check for the device. If you can see, I will be doing it for you. And I'll try to check the activity, guys. Here are the nets. If we can highlight them, shift and down arrow, you can select all these nets and right click on it and highlight with some desired color. Let us take red or orange. So now in the design, you can see these are the connected ports. So where is the block? So this is the block. And now you can see the direction of the, oh, sorry, that is how it will take the zoom, and you need to navigate it. Okay. Now you can see outputs are connected in this direction, and for that you can go to the, you can scroll with this and you can check it here as well. All these pins and ports are connected here for this memory thing. So this is the major block, RAM. And these are the blocks again. We have 32, right? 32 pins will be there. So this is the internal part of the chip. Address bar. How is the address bar written? Read, write, bus, and also address. See how are these cells available? And in the same way, you can pause and you can be seeing how these are connected with the ports. So yesterday we have connected one port called M16, which is having LED connection to it. LED on the printed circuit board. Likewise, all these pads, and again, this is a pad. You can see BRAM pad, BRAM port A. We have assigned these ports for the BRAM. So each port will go through the input and output pads again. So these pins will be sitting at the edge of the chip, and you can see the connectivity in this way. Got it, guys? So this is how you design. See, all other blocks are resting out and they have no functionality. And now your chip has this functionality now. And you can, and this set of chips in the outer peripheral on the printed circuit board on the FPGA board can be connected to the external SD card drive. Can be connected. That is already there in the PCB printed board, but we need to connect the SD card, and then now we have enabled in the processor. It will work now. Whatever we give input from that SD card as a file, that can be processed in terms of data through these ports to the processing, and this is just another port, and in this processing it will store the data. and it can be connected to many other displays. For example, take it this way: in the SD card you have an image file, and that image file will be transferred to this, and from here it will be gone to the bits, and from those bits it will go to the processor, and in this processor is connected to the another peripheral which is connected to the display. In the display you will see that image. So that is how each blocks are connected, and that is how blocks will be operated in our laptops, mobiles, any other chips. So chips have different blocks inside it. So all these are blocks. Again, you can see these blocks. So between these blocks the nets are connected. How these nets are connected? It is just a overline connection, guys. Understand, this port is connected to this. That simple explanation of the connection, but they actually get connected to a wire. And draw it on the screen, but this is what looks like in the device. I hope you understood very well. And if you can see leaf cells as well, these are the leaf cells, and these are all defined in the IP integrated given by the IP vendors. So okay, now get back to the class. So you have seen the IP pads, right? Without connections I made this, and now as I am telling, if you have sent a message through this processor through the external ports in the USB device, in the USB pen drive if you have attached, and that is connected to here, and some of set of ports will go through the processing, and it will be displayed on this uh, LED board, LCD display. So that is what FPGA block diagram, or with the use of IP integrator we can develop application on the FPGA processor. So thank you guys. Any questions, please come back to us in the WhatsApp channels. I will be answering you directly. If not, I will get back to you with the answers. And thank you.